This is a Data 620, a transistorized computer from 1965. And while it may look like we're missing stuff, this is a complete system. Our CPU is all the way on the top. We have a front panel right here. We have core memory and an ASR33 teletype. This provides I/O as well as the ability to load in programs via reading paper tape and store software out via punching paper tape. Now, where we left off last time is we just barely got the power supplies up and going. I'm feeling a little frisky today. I want to try and get spicy electrons all the way up into the CPU. Now, there's a massively long road that we got to cover to get there, but I have an ace up my sleeve here, and that's because I have the weirdest, nerdiest group of friends standing behind the camera today to help me out.
Hello, world.
Oh my gosh, you guys are so weird. But these are some of the smartest people that I've had the pleasure of hanging out with. They're absolute legends, and I think today, with our powers combined, we can get this thing doing something exciting. The Data 620 here is composed of 5 different modules. Up here at the top, we've got the 5004-1A. This is the CPU. Below that, we have 5004-1B, which is the logic power supply and front panel. Below that, we have 1C, which is the core memory. Below that, we've got 1D, which is I/O. And on the very bottom, we've got 1E, which is the memory power supply. Now, our primary goal here is to try and figure out what power goes where and how we can power things up. But it's important to note that we are not going to touch the core memory at all, because it might very well have the last known good software for a Data 620 anywhere in the world. The memory power supply on the bottom is the only place that AC comes in. From there, AC is also passed through to the logic power supply up here. And in the previous episode, we did get these interconnected and powered up, and we saw that there were some lights going on. But this is where our documentation runs out. We don't know the pinout of these 2 connectors on the back of the logic power supply. What we got to figure out today is the pinout of these connectors, which means we got to sit down and kind of reverse engineer what's going on. Then we can bring the power supply up just like we did in the previous episode. Check if the voltage levels make sense. If they seem sane, we're going to put a dummy load on the power supply and then check them again. And if they still seem sane, then we'll plug it into the CPU and see if something exciting happens. But we can't just put power into the CPU because we wouldn't know if anything exciting is happening anyways. We have to get data from the CPU back down to the front panel. And that's why we have these massive data connectors here on the back. Before we do anything too exciting with spicy electrons, we have to fix some cosmetic stuff going on up here. The CPU still looks really dingy. Also, we've got some weird mounting problems. And this is something I've been kind of avoiding for a while because it's not a one-person job, but thankfully I have 3 more people here to help me out. But we have some other problems, and if I pull the CPU out here, it does this really cool thing where it opens up like a book. And while this looks beautiful and amazing, there's a couple of concerning things going on here. Notably, we have 2 connectors right over here that have just been pulled out of the card edge. So I have no idea where those go, and everything is the same color, so we can't even really suss out what these are supposed to do. Even if everything else on the system worked perfectly, there's a good chance that the CPU is still going to be unhealthy because of these disconnected wires. However, for what we're doing today, this panel right here is going to be a godsend because this has so much available on it. I would love to get the scope plugged into these basic timing signals up here and maybe see some wibble wobbles. But we're kind of getting ahead of ourselves because top tier priority is try to make sure that we have the correct voltages coming to the back of the CPU here. The primary problem that we're running into is a lack of documentation. The only thing that we actually have is the full manual for the memory power supply. Most notably, we don't have any clue what the logic power supply is supposed to be putting out. But we can kind of figure out what it is supposed to be putting out by looking at the memory power supply. If we look at this page here, which is the very first page of the memory power supply manual, we can see that the memory power supply supplies the following outputs. plus 43 volts for X and Y drive voltage, plus 28 volts for the inhibit voltage, 0 to minus 10 volts for the threshold voltage, plus 6 volts for logic, minus 12 volts for logic. Then we have memory fan voltage and line voltage sense that are AC lines that we don't really care about. But the core memory uses logic cards just like this one that I pulled out of the CPU. And the logic voltage is plus 6 and minus 12. So I think what we need to do is we need to pull out the multimeter and start beeping out from what we think are the power rails on the cards to the connector on the back. And because the power connector on the back is keyed in a very specific way, we can then use what we learn about the power connector on the back of the CPU to translate that down to the logic power supply. So we have a bit of a game plan. I think it's time to get to work. First things first though, when we left off in the previous episode, the cooling fan on the memory power supply was making a horrendous noise. Coley rose to the task of getting it changed out though, but Coley also got to learn firsthand just how heavy the memory power supply is. With it on the bench finally, he got to work removing the 8 screws necessary to separate the fan from the case. Unfortunately, none of these screws have captive nuts, so you got to contort your fingers into a tight space to keep pressure on the nut. But once the grill and mount are removed, it's just 4 more screws to separate the fan from the transistor tunnel. Clearance is so tight around the fan that there actually wasn't room for a plug. Once we have it desoldered and out of the way, we'll solder in the new replacement fan. Then Coley had the lovely task of trying to bolt the whole thing back together. While he was struggling with that, Nevitz, AJ, and I turned our attention to the CPU cover panel. A little steel wool goes a massive way towards cleaning up the exposed aluminum. And this goes so immensely faster with 3 of us working on it. After the aluminum was looking all new again, I had to do something about the tape residue and marker on the front. Initially I tried scraping the tape off, but it was still sticky, which means it was time to break out the Goo Gone. I just worked it into the residue with a rag and let it soak in for a little bit. Then I went back over the area with the razor blade and the residue came off with beautiful ease. To get the marker clean, we just used a lot of simple green and elbow grease. Y'all had a lot of great suggestions, but I wasn't sure what kind of paint this was, and I knew that simple green was safe to use. And the results speak for themselves, I think. It looks great. Finally, we got to get the panel gap squared away. I'll loosen up all the mounting hardware and then pull out a big hammer and tap it into a better position. It was extremely finicky because the top bottom mount rails things they're a nightmare. But I think it came out looking pretty good. The panel gap is consistent and the CPU can slide in and out now without crashing into the front panel below it. Next, let's see if we can figure out what pins are what voltages. At the back of the CPU are these massive bus bars. Ground is the innermost and the outermost is not connected to anything, so we just got to figure out the 2 in the middle. To do this, we just used the multimeter to figure out which rail was connected to what pin. These little screws go through and cinch down on the rail, making them a good point to check from. And we're moderately certain that power is on the big pins of the connector here. Lots of double checking and cross-referencing and measuring later, and we're starting to get an idea of what we think the pin out of the connector is. Since we know where ground is, let's get a multimeter on the power supply side plug, and I'll just do this by connecting up some alligator clips, and then we'll flip the power switch on and check that out. 6.5 volts, that looks spot on with what we were expecting. Let's flip the power off, move the clip over and check the other pin. And heck yeah, minus 13.5 volts. That's a little lower than I would have expected, but probably totally fine. However, this is all unloaded. So let's get a dummy load on here and see if something breaks. I'm putting a 15 ohm load on the negative 12 volt rail and a 30 ohm load on the plus 6 volt rail. That may seem backwards, but we're pretty sure the negative 12 volt rail is the primary logic rail and the plus 6 volt rail is just for bias. So the current capabilities of each are going to be pretty different. Checking the voltages with the load on and powered up, we're seeing minus 13.1 volts, which is definitely a bit closer. And on the 6 volt rail, we're at plus 6.5 volts still. It looks really stable, but let's pull the scope out to see just in case. Both voltage rails here are AC coupled, and I'm looking for any ripple at all. After zooming in a whole lot, there's less than 50 millivolts of ripple on both rails. This is a massive victory. Our power supplies look to be really healthy, which means it's time to start plugging things in. We'll start with the power cable from the logic power supply to the CPU. All the power and data cables have to route around the side, in between the cabinet side panel and the components themselves. It's super tight, very finicky, and kind of a pain. But once in place, I'll hook it up to the CPU, screwing the connector tightly into place. Now we got to figure out which data connectors hook up to what, but y'all pointed it out in a previous episode. These things are actually keyed. I don't know what the right terms are, but we've got innies and outies on the edge of the connectors here, and these are all unique. Some of them are threaded so the cable can be cinched down nice and tight, but otherwise all we got to do is make a list of the organization of innies and outies for each connector. For simplicity, I listed them as ones and zeros, 1 being an outie and 0 being an innie. And with that, we were able to figure out a full interconnection diagram for the entire machine for both power and data. With this roadmap, we can get the right stuff plugged into the right places. We just gotta find the right stuff first, which means it's time to pull out all the data cables. The first step is just looking at the connectors themselves to figure out what is what. It's a little confusing at first because we gotta invert it from what's on the computer itself, but we eventually found the correct data cables. And since they were absolutely filthy, out came the Simple Green and Scotch-Brite scrubbies to clean them up. We want to save as much of the original sheathing as we can, so a little bit of teamwork makes the dream work. Everyone got involved with getting these things looking like new again, but some of the cables had sheathing that had split over the years. So the next step was to cover the splits with electrical tape. We're not going to cover the entire loom in tape, just the parts that have split or cracked over the years. With the cables looking nice and clean, it's time to get them plugged into the machine. The screw locks are great and really give an affirmative connection. Then we can start the long and arduous battle of trying to route these things through the incredibly tight space on the side of the machine. I'm already struggling with just the first one. Once they're all installed, it's going to be a nightmare. But the cable mostly finds the right place, and we can cinch down the connector on the front panel. Then it's just rinse and repeat for the next 2 cables. There are 3 cables in total that go from the CPU to the front panel, which makes sense. There's a boatload of lights to illuminate as well as push buttons to interpret. This is actually more signal intense than the communication with the core memory. The moment of truth has arrived, and we've done as many double checks as I think we can. And really, if we put it off any longer, we're just procrastinating. So it's time to throw some spicy electrons in this thing and see what happens. This will be the first time in who knows how many decades that electricity is being applied to this CPU. Now, this computer spent a decent amount of its life down at NASA at the Manned Spacecraft Center. So it feels only appropriate that we do a proper go, no-go check. So, go, no-go check. Memory power supply.
Go!
Front panel.
Go!
CPU.
Go!
We are go. Memory power supply, give me power on. CPU, give me power on. We got lights! Yes! That's what I'm talking about.
Yeah!
Look at that. High fives all around.
That one. We'll go back. We'll go back. Right.
There it is.
It did something.
It did something. It didn't blow up. All right, after we all calmed down a little bit, because, I mean, let's be honest, that was pretty exciting. We sat down to try to figure out what worked, what didn't work, and, you know, obviously a lot doesn't work. And as soon as we cut all the cameras off, it popped a fuse. This is a 2 amp slow blow that's on the logic power supply, and it's very much so blown. I don't have a replacement 2 amp slow blow, so I slipped a 3 amp in there, which is a little overrated, but should survive whatever inrush current it's fighting. And I think it's come back to life. Yeah, so we're mostly back to life, but things are not healthy. And of course they're not healthy. The thing's crazy old, and it doesn't have any memory hooked up to it. Like most of the switches don't do anything. I can turn that switch on, and reset doesn't clear it, but reset up here does clear and change some stuff. So I can, you know, set those 2 bits in the A register and I can clear them, but I can't do that with anything else. So, like I said, it's super duper unhealthy, but it does seem to be showing signs of life, which is very exciting. With it powered on, let's get a look at the voltage rails. The negative 12 volt rail is sitting a little higher than I would like, but being within 0.8 volts or so is probably okay here. However, we can't seem to find the plus 6 volt rail at all. It appears to be completely dead. That's not good. Let's disconnect the power cable and check it at the power supply without load. And yeah, we still have plus 6 volts here. All right, the next question is it the power supply or the CPU? Let's check the resistance between the 6 volt rail and ground on the CPU. All right, yeah, 0.3 ohms. That's a dead short to ground. Something failed on power up because we didn't see that before. There's a short on one of these logic cards, but we don't know which one. I think the best way to tackle this is going to just be removing every single card methodically. We set up a sort of assembly line with Nevitz removing cards, Coley labeling them, and AJ stacking them. Once everything was removed, I took the opportunity to give the cage a bit of a clean. I used a paintbrush to wipe away any dust that had accumulated over the years. Then I went through and sprayed every socket with deoxit, both to make it easier to install the cards as well as hopefully get a clean connection. Then we did the whole assembly line thing in reverse. Coley was in charge of organization and checking for faults. AJ and Nevitz were cleaning the cards rigorously, and I was plugging them back in one by one. Everything was in surprisingly good shape, and just a bit of cleaning with the paintbrush got the cards looking good again. To suss out the fault, we hooked up the multimeter between the plus 6 volt rail and ground. Then each time we plugged a card in, we'd check the resistance, and sure enough, after just a handful of cards, the multimeter dropped down to less than 1 ohm. Looks like we found our short. The offending card was this one right here, card number A21. Now, that might not be the only one that failed, so we continued on with our methodical plug-in and check assembly line. Each time we plugged a card in, we could watch the multimeter drop a few ohms as more and more components ended up in parallel across the rail. All in, the process went really quickly with all 4 of us working in unison. The last card went in and no more shorts. All right, well, that was enlightening. We found 2 bad cards. One of them we found almost immediately, and that's this one, A21. This is the one that had that dead short to the 6 volt rail. So something on here has gone bust. My guess is that maybe one of these electrolytics has gone bad, or who knows, maybe we've got a bad germanium transistor on this guy. But while we were going through and cleaning up the rest of the cards and getting them slotted back in, we came across this one, which has 2 transistors that have just completely rusted off. I don't know what either of these boards do. This one's labeled a GA27-1. This one's labeled a PA24-2. Now, it should be noted that all of these cards have a massive number of germanium transistors and, more worryingly, germanium diodes. When we did the Bendix G15, we tested around 3,400 diodes and we found about 60 of them were bad. I'm expecting this thing to have more diodes than the G15, but probably the same failure rate, which means that we're looking at, I don't know, maybe something like 100 plus failed germanium diodes. But I don't have a good way to test these. With the G15, we had this like lovely diode tester where we could plug packs in and test each individual diode, and we don't have anything like that for this. So we're just gonna send it. I'm gonna go and see, I've got a couple of spare cards. I'm gonna see if I can hunt them down. If we have duplicates of this, we'll just toss the duplicate in. If not, I'll salvage some transistors off of the duplicate card. We'll find the short on this one. We'll get both of these at least somewhat repaired back into the CPU, and then we'll power it up and see what happens. There was another GA27-1 in the I/O box, which I'm gonna liberate for the time being. The I/O box is already missing a lot of cards, so that's a problem for future David. We checked the replacement for shorts and then slotted in place in the CPU. We didn't have a spare PA24-2 though, so we're going to have to repair it. Coley took the reins on this one. The legs from the bad transistors were still in place, so he would heat the solder up, then extract the leg like pulling a metal splinter. My hands are not anywhere near steady enough to do that. We decided to pull 2 transistors from the shorted board that we just replaced. I used my trusty Radio Shack desoldering iron and a 90-degree pick to get them loose. Then tossing them over to Coley, he slotted them in on the PA24 board and then fully soldered them into place. The board has been freshly repaired, although any number of components on this thing could still be bad. And with all cards populated again, let's power it up and check the 6-volt rail again. Excellent news. The 6-volt rail is back. All right, we've been pushing some buttons here and interesting things happen. So right now you can see the run light is on. If I hit reset, the run light comes off. And now it seems like we have some semblance of control up here. So on the A register here, if I hit the reset button, look at that, we cleared the A register. Now I would do that for the B register, but the reset button's broken. Oh my gosh, I just pushed it all the way in. All right, that's something for David to fix in the future. For the instruction register, we can reset it too. We can reset the instruction counter, but it looks like we got a stuck bit over here. We can reset the index register, which is kind of cool. But so now that we have these reset, I can go through and set the bits again. And that button's broken. Some of the buttons press, but the lights don't come on. I'm thinking that probably means that we're actually setting the value, but the bulbs are burned out. And, you know, who knows what's going on here. But then I can do run, and it does stuff. I don't think it's doing the right stuff. So there's like real deal computing going on. Okay, we pulled the scope out and we've been probing around on this little engineer panel that's here on the front, and we're discovering some pretty exciting stuff here. First things first, let's check the master clock right up here. And you can see it is chugging right away. And if we reach over here and we press measure, we can see that the master clock is chugging along at 2.2 megahertz. This thing is moving quick. That's pretty exciting. However, if we go back to run here and we check CL1, it's totally dead. CL2, that's also totally dead. EPH is dead, but PHC has something going on it. However, the CPU is currently halted. I hit the reset button here, nothing is running, nothing is going on. So it's not actually that surprising that CL1 and CL2 are totally dead. So let's try to tell it to run something. Now there's no core memory in this, so it can only run one instruction, I think, and that's whatever we manually put in the instruction register here. I think if we do a reset, we set the instruction register to all zeros here, this should be a halt instruction, which means that when I press the run button here, it's going to execute the halt instruction, halt the CPU, but put it into a mode that allows you to step to the next instruction by pressing the step switch. So something is now going on within the CPU, because if we check CL1 here, you can see we have activity on it. Same with CL2. But let's take a look at the computer bus now. So I've got a little thing here that I can clip onto for bit 0. This should be our least significant bit. And you can see that there is indeed activity going on the computer bus, which is pretty exciting, right? But check this out. If I hit step here, we can see our instruction counter goes ballistic and the activity on the bus changed. So I think that means that this Data 620 just executed an instruction. It may have been the wrong instruction, it may have done completely chaotic, dumb stuff, but hey, this thing just ran something. So the goal this morning was to throw some spicy electrons at this CPU, and this CPU has received those spicy electrons with grace and, well.
Grace and mercy.
Grace and mercy.
Grace and mercy.
No, it hasn't.
Hallelujah.
It's like approaching midnight. It has been an absolute blast hanging with these 3 legends. We've got my good friend AJ here from Forgotten Machines. We got Nevitz hiding out underneath the CPU over there. We got Coley on the far end. It has been absolutely legendary. The Data 620 is making fantastic progress. I am extremely excited about what's coming up next on this project. So I want to thank you all so much for watching, and I hope to see you in the next one.